Welcome to Daily Papers, the podcast where we break down fascinating new research into bite-sized conversations.
Today, we're looking at a paper with a fantastic and slightly worrying title, Benchmark Success, Clinical Failure, when reinforcement learning optimizes for benchmarks, not patients.
It sounds like a cautionary tale. It brings up this image of an AI student who gets a perfect score on their medical exams, but then has no idea what to do when they see a real patient.
That's exactly what this paper is about. The goal is a noble one, to train an AI that can help radiologists read chest x-rays, potentially spotting diseases faster and more accurately. To do this, researchers are using some of the most powerful AI tools we have.
Right. They're using what are called vision language models. You can think of these as AIs that can both see and talk. You show it an image, in this case a chest x-ray, and it can write a report about what it sees.
And the big question is, how do you train it to be really good at this? The method these researchers tested is called reinforcement learning. It's a very popular way to train AIs.
We can explain that pretty simply. Reinforcement learning is basically like training a dog with treats. When the AI looks at an X-ray and correctly identifies a problem, it gets a reward, a high score. If it gets it wrong, it gets no reward or even a penalty.
Exactly. The AI's goal is to get the highest score possible. Over thousands and thousands of attempts, it should theoretically learn to make better and better diagnoses to maximize its treats.
So the researchers set up a two-stage program for their AI. The first stage was called supervised fine-tuning. This is like giving the AI a study guide. They gave it 2,000 X-rays, but also gave it a perfect step-by-step analysis to go along with each one.
It's like a medical student following an expert doctor, learning to copy their reasoning. First, look at the lungs. Second, check the heart silhouette. Third, the AI learns to imitate this expert process.
Then came stage 2, the reinforcement learning we just talked about. They took this book-smart AI and told it, okay, now go practice on your own. They gave it another 1,000 X-rays and started rewarding it for correct diagnoses. The idea was to sharpen its skills and make it even more accurate.
To see if it worked, they tested the AI on a big, standardized dataset of X-rays called CheckSpurt. This is the AI's final exam, its medical boards. And the results, at first, looked amazing.
They did. After the reinforcement learning phase, the AI's performance on the CheckSpurt test shot up by 23%. By all measures, it was a huge success. The AI had passed its exam with flying colors.
But then came the twist. The researchers decided to give the AI a surprise test. They showed it a completely different set of X-rays, this time from the NIH, a different hospital system. These X-rays were taken with different machines of different patients and labeled by different people. It was a test of how the AI would perform in a new clinical environment.
And it completely failed. Its performance didn't just stay the same, it plummeted by 19%. This is the benchmark success, clinical failure. The AI aced the official exam, but was completely unprepared for the real world.
So what went wrong? The AI hadn't actually learned the deep principles of radiology. It just learned how to be really good at that one specific test, CheckSpurt.
It was like it learned shortcuts. Instead of identifying pneumonia from the signs in the lungs, it might have picked up on some random, meaningless clue in the test data. Maybe it noticed that images from a certain machine used at the first hospital often had a particular issue, and it learned that association.
That's a classic problem in AI called overfitting or learning spurious correlations. The AI finds a pattern that works for the training data, but it's not the right pattern for the real world. So when the data changes, the AI is lost.
And here's the most fascinating part of the paper. The researchers looked back at their training process and found something incredible. The AI, before it went through the aggressive reinforcement learning, the one that had only completed the first study guide phase, actually did better on the new hospital's data.
That's a total paradox. Making the AI smarter for the test actually made it dumber in a real-world scenario. The initial teacher-guided training seemed to give it a more robust, generalizable foundation of knowledge.
But the second phase, the reinforcement learning, basically trained that good foundation right out of it. The AI became obsessed with chasing a high score on the test, and in doing so, it forgot the fundamental lessons and started taking those silly shortcuts.
It also depended on the AI they started with. They tested a general-purpose AI and one that was already pre-trained on medical texts. The general AI needed a very strict step-by-step checklist to learn anything, but the medically trained AI actually did better when it was given more freedom because it already had the background knowledge.
So, what's the big takeaway here? It feels like a really important lesson for anyone building AI, especially in critical fields like medicine.
The lesson is that chasing high scores on a benchmark isn't enough. It can even be misleading. You might end up building an AI that looks brilliant on paper, but is too brittle to be trusted with real patients from diverse backgrounds and hospitals.
So, for something as important as healthcare, maybe this slow and steady approach is better. A careful, curated training process that teaches the AI how to reason might be more valuable than an aggressive training method that just pushes it to get the highest score, no matter how it gets there.
Exactly. It's a reminder that with AI, it's not just about getting the right answer, but about getting the right answer for the right reasons.